So thank you for everyone for attending today's webinar. I just want to introduce our speaker, which is Peter Lawrey. He's the CEO of Chronicle Software. He founded Chronicle in 2013 as he saw a great demand for low latency Java within electronic trading. During the past 9 years, Peter's been pivotal in growing Chronicle Software to become a trusted partner to many global tier 1 banks and hedge funds. And in addition, Chronicle Q open source and our other open source libraries get around 24 million downloads per year and is used across multiple industries ranging from payments, biometric research and gaming consoles. Prior to this, Peter had many senior consultancy positions for global financial institutions, including RBS, Barclays, UBS and Reuters. He's a Java champion and one of the global leading experts in Java development with the most dance on Stack Overflow. He's driven the use of Java in low latency trading, opening up the skills and capabilities required to build the most demanding app. He continues to research and develop innovative ways to utilize Java within this low latency microservices architecture. So the format of today is that Peter will give the presentation. We'll have a Q&A. If you have any questions during the presentation, please submit them via the Q&A or chat feature in Zoom, and we'll answer them at the end. So over to you, Peter.
All right. Yeah, thank you everyone for joining me over your lunch break or whatever time it is where you are. Today's talk is on a number of things to do with low latency Java, but also about developing efficiently. Our products are widely used for mostly in tier 1 banks, but other financial institutions. We do have some use cases outside that arena, but most of our revenue comes from tier 1 banks. Key thing that we're looking at today is some of the ways in which we help our clients transform how efficient not just the servers are, but the developers are and development process. So we can take a project that may have taken 2 years and 20 developers and then turn it around in 6 months with less developers. If you've got a system that's taking 3 months to get new features out, we might be looking to do that in a couple of weeks. A lot of people's mindset is in microservices is to think about it in terms of milliseconds, in terms of latency. We're looking to provide, and we do provide microservices that are in microseconds. And we also look to provide systems that are vertically scalable. That is, that they have a lot of headroom to scale up within a single machine rather than having to have many machines horizontally scaled. The problem we're looking to solve here is to ensure that we've got clear requirements so that we have timely and effective development, manageable project risk, and performance is one of the functional requirements of the project. It's not just an afterthought we get it working and then we worry about performance later. It is a first-class requirement of our applications. So today we're looking at initially at ways in which allocations don't scale, and this is a lot of the reason that people end up using lots of machines to get more performance, because running more application on the same machine doesn't give them doesn't increase their performance, and a big source of that is bottlenecks. One of the key bottlenecks in Java, at least, is in allocations. Another one is about accidental complexity and showing how taking a completely different strategy can significantly reduce your overheads in terms of both the execution of the software, but and also in development. And lastly, we look at some actual code examples. How is it that we make developing and particularly creating tests for these applications easier? So the first thing that we're talking about today is about allocations. And the reason I focus on allocations is that there is a perception that because GC times are generally manageable and that GC is the main problem, that You don't need to worry about, well, we create lots of objects. That's not a problem. When in reality, particularly in short-lived objects, the cost of allocating those objects can be 80 times the cost of the GC pause itself. And because this is a very much an underrated impact of creating lots of objects. Part of the reason for this is that if you look at benchmarks like JMH, which is a very, very good benchmark, it's single-threaded. So typically, so as a result, it doesn't show up what happens if I try and use more threads at the same time running this software. How do they impact each other? How do they get in each other's way? It's not really a question it's looking to answer. Also, when you're doing testing and deploying, often you're focusing on just how your application is behaving. And if it's using up to 4 cores, then you may not see any impact of allocations. It's only when you try and use all the cores on a larger machine, or you're running on, you've got a virtual machine that might be quite small, but it's running on a bigger machine, then it starts to have a significant impact. So this is a test. So a lot of the details about what was actually done and how you can run this yourself are in the articles. There's a link at the end. So you can run this code yourself, but this is a benchmark where it's just creating lots of small objects. They're about 50 bytes each, and if you as you use more and more cores, go from 1 to 2 to 3 to 4, the latency for each allocation is about the same. And in fact, your throughput goes up, which is what you would expect. However, if you go beyond 4 cores, and on some machines it's only 2 or 3 cores, you find that you've saturated the system's ability to create more objects. And then as you try and use more cores, what happens is it just takes longer to do those allocations, until eventually on this machine, running it across 32 threads, you end up, it just takes 10 times longer. And if you've got an application that's bottlenecked on allocations, you won't get any more performance out of using 32 core threads as you will for using 4, which is obviously a serious issue in terms of scalability. So let's look at a more realistic example. So part of the reason is that while each core can run independently, they're using shared resources, which is both L3 cache and access to memory. And so once that is saturated, you don't get any more performance by adding more cores. And what you really want is those cores to run much more independently of each other, so that you actually get full use of the whole system. So let's look at a more realistic example. In this case, this is using our channels library functionality that's in Wire and Q. It's part of the open source. You can run this test yourself. If you've got 16 clients talking to 16 services or 16 threads running the service, and all it's doing is it's sending an object or an event to the service, and then an event is sent back. So it's just echoing a small, simple event with the option of creating an object each time. So we'll look at the difference of creating one object versus creating no object. So the default behavior for our libraries is that sending and receiving objects or events doesn't create garbage at all. But what is the impact of creating just one object? So this is an example of, these are very simple objects just to, just to keep them lightweight. The objects themselves, these are all actually primitives under the covers. So the object is only 44 bytes long, but to keep it efficient. But as you can see, it's somewhat realistic in terms of the data. You've got doubles, you've got numbers, you've got text and timestamp. So the center column shows how it performs. So it's getting about 4 billion events a minute, which is not necessarily a requirement in most cases, but it's just the fact that you're trying to use 32 all the threads on the machine. at once. And if you use all the threads on the machine at once and you don't create any garbage, then you can get around well over 60 million events a second. Notice that there's a slight improvement between Java 8 and Java 11, but beyond Java 11, there's not a significant improvement, possibly a slight improvement in Java 17. Now, if we create just one object each, you can see that the typical latency, the average latency, increases by roughly 150 nanoseconds, as we saw in the other benchmark. 150 nanoseconds doesn't sound like a lot, but it's actually sapped 25% of all the throughput. Now, by comparison, the GC pauses takes 0.3%, so it's spending 0.3% of the time doing GC pauses, but 25% is lost just by allocations, and so that the overhead from the allocations is about 80 times the overhead from the GC pauses themselves. Now, let's say, is there an easy way to work out, rather than doing all of this kind of work and so on, is there an easy way to work out, estimate how much time is you're spending in allocations on a given system? Well, a lot of high-end systems actually have fairly similar allocation rates they can support. So a high-end laptop can handle about 8 gigabytes a second. A typical server is about 10 gigabytes a second. A high-end desktop, such as a Ryzen, can handle about 12 gigabytes a second. There's not a lot of variation there. So if you start with 10 gigabytes, partly because it makes the calculations easier, then what you can do is you add up the allocations of all the JVMs on a physical machine. So it's not by virtual machine. As I mentioned, it's not isolated by virtual machine. It's the total for the whole machine. Say it's only a gigabyte a second, then you're spending about 10% of your time allocating objects, which is perhaps not a huge concern for you, depends on your use case. However, if you find that that allocation rate is closer to 10 gigabytes, then you might find that any reduction in allocations can result in an increase in throughput that you can achieve. So I've seen this a number of times where a system is saturated at about 10 gigabytes a second, and a 10% reduction in allocations results in a 10% increase in throughput. And I've done that in some cases many times before eventually it starts to drop to like 8 gigabytes a second instead of 10, and then you're not getting quite as much improvement. But you can reduce your allocation rate quite a lot. And anything you can at this point, when you're saturating your allocation rate, anything you can do to reduce it will result in an increase in throughput that you can achieve, as well as a reduction in latency in terms of the time it takes to execute those tasks. So in short, if you're trying to use more than 4 cores at once, allocation rate may be an issue for you. So have a look at your total allocation rate. And the other key point is that virtual machines don't give you any partitioning for this. So if you've got a single 4-core virtual core instance running on a machine, that can be enough to saturate your allocations for the whole machine. And so it's something you may need to watch out for or take into account. So moving on to accidental complexity. So accidental complexity is where your system is spending time doing things which are not essential to the task at hand. So what is it that you actually need the application to do? This is not always apparent as to how much accidental complexity you have unless you compare it against another system doing exactly the same thing, or at least both of them are achieving what your end goal is, but one is a lot faster than the other. So if you compare the performance of the two, you can say that the difference between them is accidental complexity. Now, it's possible that what you're comparing against itself could be more efficient, so the number may be even higher, but one way to determine if a system has a lot of accidental complexity is to compare it against another system that also is satisfying your requirements. So then the difference is doing things that you don't necessarily need. So let's have a look at a concrete example. Oh, sorry. So how is it possible that you could have very high levels of accidental complexity? Well, a system typically has many layers of abstraction. Each layer of abstraction will do more or less what you want it to, but often does more. Sometimes it might be 10% more. Sometimes it might be 100% more work than is actually required. But because you've got multiple levels of abstraction, that can multiply together. So if you've got 10 layers, each one of them's doing roughly twice the work that it needs to, then between them, you can end up with 1,000 times the overhead of actual work done that you need it to do. So let's have a look at a concrete example. So this is a comparison between two ways of doing messaging. In both cases, you've got a process that's writing to a queue, another process that's acting as a service, listening to that queue, and just echoing. Again, it's another echo service. We're not benchmarking the service itself. It's sending that event back again to a different queue, and then that's being picked up and received by the original client. And then what we do is we time the round trip time. In similar tests published for, in this case, we're comparing Kafka, which is intended to be used for low latency. It is used for high throughput very often. There is a number of latency benchmarks published for this. In particular, I'm having a look at the 2 nines, which is worst 1 in 100. If I share this again. So the worst 1 in 100 is the 99th percentile here. So that's a lot of latency benchmarks will show that. So 99th percentile means that 99% of the results are less than this, and 1% of the results are that or more. A simple way to do that as an algorithm is to take all the timings, sort them, and then take the 99th percentile, or the near the end, the highest value. So so this result is about half what I've seen in many benchmarks for Kafka. So I think that it's not unrealistic. So you always take when one vendor compares to another vendor, you take it with a grain of salt. But I've compared it to other published results for this product, and those results are actually half of what they publish. Whereas by comparison, so we've got here what looks like a fairly large number, but that's because this is in microseconds. So it's 22.6 milliseconds, and Chronicle Q Enterprise is getting about 3.7 microseconds. Now, both of those sound pretty fast. So how might you compare it because you can't see these latencies? How might you compare them in a form that you can see? One way to do it is to look at not in terms of time, but the distance a signal could travel in that time. So how far could a signal travel in 2.6 milliseconds for comparison purposes? And the ratio between these two solutions is about 750 times in this situation. So if we compare the distances, 2.6 milliseconds is the same. You could send a signal from London to Dumfries in that time. So across a good portion of the United Kingdom in 2.6 milliseconds. So then you get an appreciation for distance and that signal can travel. How much could you do in that time? But if you compare that to what Chronicle does, about 2.7 microseconds, we're talking about the distance of a short walk across London. So a couple of blocks in London. So you can see that they're quite different. I mean, even this seems like a long way. If you were to look down this road, it would seem like quite a distance. So it's not like that isn't actually doing quite a lot in that time as it is. Why does this matter? I mean, because you might say, well, we're not in a low latency space, so it doesn't make a lot of difference to us. Well, actually, it's not just in production does it have this impact, but also just in developing your software. So if you have to run hundreds or 1,000 tests, and you have to start and stop the service each time, then that's going to take a very long time to do, because the service is has so much mass to it that it takes a while to start, takes a while to run, and it takes a while to shut down. Whereas if you've got very lightweight services, they're very quick to start, very quick to test, and very quick to shut down. You can run through many tests in a short period of time. And that means your whole development life cycle is shorter between when you've made a change and when you've run, say, all the tests, or at least a number of the tests, to see that it's worked. And then you can go back and change it again if it hasn't. So this is our EFX platform, which is used for foreign exchange. It specifically has 466 tests. So, but to run, to build it, run all the tests, build a Java doc, takes 71 seconds. So each test is taking in the order of about 1/10 of a second, which means you can run through hundreds of tests in a very short time frame and not slow down your development life cycle so much. To actually run a test takes, or a small batch of tests takes about a few seconds from an IDE, and so again, you've got a very efficient development life cycle. And because it's lightweight, everything can be run on one machine, just on your development PC. You're not having to go off to external resources. You're not having to get access to some database. You can do it from a laptop pretty much anywhere, even without the internet, because everything is self-contained. So that means that you can be more productive. You're not as dependent on others and all the state of other systems to do your development and testing. Some key takeaways is a general rule of thumb. You can, by tuning a system or a piece of software, you may be able to reduce latencies by 50% or increase throughput by 100%, like basically a factor of 2. But if you use a different strategy, you can transform your performance but also the efficiency of your development by sometimes orders of magnitude. And a number of times in my career, I've seen improvements of 100 to 1,000 times by doing fairly simple things and transforming the way the software is developed and also run. So one of the downsides of all of this approach can be that it can be cumbersome to work with, or difficult to work with. So we've gone to great effort to make it also, even though it's highly performant and efficient, that it is still easy to develop and test and work with, even if you're not a low-level Java developer. We can still use normal Java. So this is an introductory example. We've got an article for this on our blog, on our website. We're working here at just the level of a Java interface. So we have one simple Java interface that has one argument, one method with one argument. And now we've got in the middle a function. It's a very simple function. All it does is it adds an exclamation mark to any message sent, and it sends another message with that exclamation mark. This is a template for how all of our microservices work, or how our gateways work. There's a method for each event type. It can produce certain events out, and the handle or proxy for where events should be written is passed in either via a constructor or a setter. So because we're dealing at a very high level of abstraction, we can model this as YAML messages in and out. So on the left-hand side, we've got a series of YAML messages that then in turn produces another series of YAML messages. As you can see in the text, it's all got an extra exclamation mark. Okay, so I had a little question. Can we talk more about how not to create objects? Okay, so we'll definitely come up with some more examples as we go through. Okay, so so in this comparison here, if we change the input or we change the code, we can, and because we're texting, comparing YAML output against an expected YAML output, we can very easily see any kind of discrepancy. And it makes maintaining the test very easy, because if this is now the new expected behavior, we can just take the result, overwrite the input, and then proceed. Okay, so let's get into a more realistic example, which has some examples of how we reduce garbage. So in this case, the blue shapes are the queues, which are messaging between different microservices. The orange boxes are microservices. And in particular, the order system is taking new order single, which is based on a fixed message, and producing an execution report. So so in this case, we've got a new order single. Now, we could use a string for our symbol. However, because the symbol is short, instead of using a string, we can encode it as a long. And because it's a long, it's now a primitive and it doesn't create any garbage. Another key thing that is that when we read messages coming from off the network or off a queue, the objects involved are implicitly recycled. So as I mentioned before, we can run long series of message processing without creating any objects at all. Part of that is in the deserialization, we avoid creating any objects. And we implicitly recycle them. So in this case, as a new order single comes in, the new order single object itself is recycled, so that doesn't create an object. The symbol isn't even an object because it's a primitive. So it's a string of up to 10 characters encoded in base 85. Base 85 is the largest base you can have that fits within a 64-bit value for 10 characters. So it is a nice compromise, and it supports most ASCII characters that you might want to use. So you can create your own encodings, but rather than do that, you might find that base 85 is more than sufficient. Timestamps, again, instead of using say a local date time object, we use a long. So it's just the number of nanoseconds since epoch. So again, it's a primitive. It takes up less memory. There's less indirection, and there's no object being created. Our prices, our quantity and price are doubles. So again, they're primitives. There's no big decimal being created or big integers, which then in turn can have nested objects. Again, no garbage being created, no objects being created, much more compact in terms of memory and on being sent across the network. So again, that saves both bandwidth and memory and allocations. Now, the next one is a side, it's an enum. Now, even though it's an enum, it's not creating any new objects because all possible enums are created when the class is loaded. And because it's created when the class is loaded, that doesn't create any new objects. Now the string, now this is an interesting one, it's the client order ID. So the client order ID, if you create new client order IDs, and often you have very little control over it, that can result in new strings. However, if that client order ID is reused, then it implicitly uses an object pool for the strings. So you can that can reduce but not eliminate garbage. Now we have alternatives where you can store strings in reusable objects such as string builder, for example, or bytes. However, that's not generally used, mostly because if you've only got one field that's creating garbage, and that's a Java, and that's an order, even most exchanges don't have so many orders in a day, or that it creates much memory pressure. Because as I mentioned, you want to watch your allocation rate, but you don't have to eliminate it completely, because if eliminating it, it just needs to be low enough that it doesn't matter. Yeah, so 2 questions have come in. In the benchmark with Kafka, do we take into consideration also the cost of serialization and deserialization? If yes, do you use the same serialization technique for Kafka and Chronicle? That is a good question, and the answer is no, we don't. So Kafka is typically used with JSON, and obviously the Chronicle queue is used with Chronicle wire. How much difference does that make? Not as much as it really you would think, because we're using I was using Jackson, which is one of the best JSON libraries, and it creates a little bit of garbage, but doesn't actually create that much. The main thing that's different about Jackson is that it's not designed for recycling objects. So if you deserialize you can't pass it in an object and say populate this object with what I've got, or at least that's not how it was used. So serialization was a factor, but not as much of it. It's mostly about Kafka and Chronicle queue, the messaging. And also the point of the comparison was really about accidental versus complexity versus essential one. So, I mean, the exact cause, I mean, you can see this kind of thing happening in other examples that are unrelated, that you can have 2 applications doing the same thing in terms of functionality, but one of them is much more efficient than the other. So if you use JSON wire, which is in Chronicle wire, you can deserialize JSON messages without creating any garbage. So we have a JSON wire which supports JSON. It also supports serializing and deserializing without creating any garbage. However, I would say that the difference between that and using Jackson, for most people, you're not going to notice a huge difference. Other than if garbage is a problem for you. If it's not a problem for you, it's not going to make a lot of difference. In our case, we use it because it's consistent with all our other libraries, and we do have a requirement to keep garbage very low. But for most applications, I'm not sure it would make a lot of difference. So I don't have an example here, but so in Jackson, in our JSON wire, we also support types. So you can send typed data as well, just like you can in YAML. So one of the reasons we use YAML is, apart from being a little bit more concise and friendly to read, it supports types and comments, both of which we use quite a lot in certain use cases. To make it the coding clearer. But in this simple example, there's only one type, so the type doesn't appear here. But nevertheless, you can see that you've got structured data, you've got quite complex scalar values, and yet very little garbage is being produced. But also, in terms of constructing the test, once you've got a test that works, you can create variations on the test. What happens if you've got two new order signals? What happens if there's data missing, or it's invalid, or you can try out those examples very quickly and see how it behaves and ensure that it's behaving correctly. Yeah, so so the question is about using string builder. So one of the downsides of using string builder, so one of the benefits of using string builder is that if you recycle it, set the length to 0, and you can append to it, then you can save creating both the string builder and the underlying char array or byte array. So that saves some garbage, but at the end of the day, you probably have to two-string it. So what we do in our libraries is that we can take a string builder without two-stringing it and still use it. But that's unusual. Generally speaking, recycling or reusing a string builder can help, but it doesn't eliminate it entirely if you're going to call two-string on it. But certainly in newer versions of Java, they've improved the overhead of append. So in many cases, append used to create garbage, but doesn't so much anymore. So you do see an improvement. There's some improvement in reusing the string builder, but I would look to see whether it shows up in a profiler. If it's not showing up in a memory profile, I wouldn't bother changing it. Yes. Yeah, so reusing the buffer is another key thing. So one of the things that Kafka doesn't do is, one of the things that Kafka does is it passes messages around as a byte array, and it creates new byte arrays each time. So that can be a significant source of garbage, no matter what else you do. I'm not entirely sure that was actually the biggest overhead. I think most of the overhead is actually in the broker itself. But I don't have good visibility on that. Okay, so if we compare, again, in this case, there was a bug in the code where the order ID wasn't being set correctly, but you can see very quickly what is wrong, where is the discrepancy between what was expected and what actually happened. And in our case, we have some tests that are like a megabyte long of YAML, like a whole series of events and complex scenarios and reference information and data. And then once that, but you can very quickly see if you've changed the code or there's something wrong as to what the actual discrepancy is. Okay, so before I move on, there's, okay, 2 more comments. Oh, no. All right. So moving on. So behavior-driven development and event-driven architecture. What are the benefits, and why do we advocate them? These are areas, particularly behavior-driven development is an area I find it's hard to get developers excited about, but it can be extremely valuable in trying to make sure that your project is on task and is doing actually what the business requires and continues to do what the business requires long after it goes into production. So business, when you start a project, business usually has a number of requirements. So if we're using orders of magnitude, they can usually tell you about 10 things to do with a project that they know off the top of their head. That'll come very easily. And you as a developer using your expertise will be able to specify another 10 requirements. Now, given a length of time and a number of iterations, you can build that up into the order of about 100 each. However, that really doesn't specify absolutely everything to do with the system, like how does it handle errors and how does it handle all sorts of edge cases. that can be very difficult to get a clear and specific requirement from the business, or even based on experience as to what that should be up front. So even though it is good to do test-driven development and start with the tests, you can only start with a test if you know what the requirements are. If the requirements aren't clear, or the requirement is it should behave reasonably, then that's very difficult to specify, because reasonable is based on what you would deem acceptable, rather than having a specific idea of what it should do. So this is where using these in combination allows you to produce a lot of regression tests which flesh out all of the detail about, well, how does it handle, if you have 3 inputs that are invalid, how does it respond? Does it respond on the first one it finds? Does it give a response for all 3 of them? Does it give some other error message? Does it disconnect? What is the behavior in that situation? Often that's very hard to clarify in advance what it should do, and it can unnecessarily lock down your system in ways that aren't really requirements from the business. They're just to specify it so that you can do test-driven development. So instead, what we do is we encourage creating regression tests to cover all of those cases, and that way you can see, not necessarily, so you can visualize it as to what is appropriate, is it reasonable in terms of what it does, and then you can become aware if in the future anything changes, that this will result in a change in the output, a change in behavior from what it was. So because it's once the software is in production and it matures, it's being aware of unintended consequences where this can add a lot of value. Yes. Yeah, we just so one of the questions, I just had a question about string buffer. I would highlight that string buffer is a thread safe, and almost always is not desirable compared to string builder. The reason is that string buffer, there's no particularly valid reason to ever use string buffer, because you either have to lock it for the whole life of its use, or you end up with a potential for race conditions, or it's never actually used in a multi-threaded context in the first place. So what we tend to do is we'll have a thread local which caches a string builder. Yes. So yeah, if you unfortunately, string buffer is still used in a lot of libraries, but it's pretty much guaranteed that a string builder would have been a better choice. And using a thread local to cache your string builder can make it so that you can share a reused string builder across multiple threads. So behavior-driven development is a methodology for creating scenarios, descriptive scenarios up front that is in the language that the business would understand. And so it is as close to automating the business requirements as you can get. That's its intent. Like I said, you should do that as much as you can, but it gets to the point where it's very hard to extract further details out of the business. So yeah, so it creates a common language. It focuses on requirements capture and automated checking of those requirements. Event-driven development. So as I mentioned before, all of our services have events coming in and events going out, whether they're gateways or whether they're microservices, and it can be made very performant. But from a design point of view, it's extremely good for creating regression tests. So, so in this example, a good example here, where on the left you have messages coming in that are being normalized to some internal format, and then on the right they're being denormalized out to the format's appropriate for an external system. So then internally you're only dealing with idealized messages that are in the form that you would prefer to be working with them. And in particular, when it comes to developing that core control system, although in a more realistic environment, you may have 10 of them, it would be more of a correct order magnitude. But for designing each control system, all you need are the input messages, because that's everything it knows, and the code. So code is essentially another input. But you can recreate the state of that control system at any point just by replaying the inputs. So this is useful for warm-up, so that you can warm up a system with realistic input data. For testing, standalone on a development PC, for creating unit tests like we saw before as a regression test. You can take an input queue or logs from production without accessing anything else in production, like a production database or any other system. You just need the logs, because that has everything in it, and you know it has everything in it because the control system only takes information from those inputs. So it's easy to build and maintain regression tests. So one of the problems with having a large number of tests can be that it becomes prohibitive to maintain them all. But because of this process, it makes it very easy to maintain a very large number of tests. And finally, you can see that we can, all of the content here is based on articles which are available on our website. So you can read up more details on them, and they in turn have links to open source code you can run to try out these things and see how it goes for you. So do we have any questions?